Voice clear है? आ रहा है ना? All right, so let's continue with the hydrogen atom. Now this is uh, hydrogen atom using quantum mechanics. Now, okay, we have semi-classical approximation we have seen, but I'm not going to go through each and every step of derivation. Okay, I know most of you might have done it. Have you, the undergraduates, have you done the hydrogen atom problem, quantum mechanics? Okay, so it's clear we have all done it. So it's like the idea is to just give an overview of the hydrogen atom problem and how do you solve it quantum mechanically. All right, so hydrogen atom, okay, let's start with the Hamiltonian of the system. As you already know, we need to find out the Hamiltonian of the system, which is actually the kinetic energy and potential energy, and the reduced mass, again, the same definition we have talked about, and the potential is the potential between electron and the nucleus, and the kinetic energy of the electron. Now this, as I said, we can have hydrogen atom, or you can solve it using the same method for helium ion or doubly ionized lithium. Okay, so I don't know, the title is coming a little later, but okay. If you have a spherically symmetric case, okay, you usually use spherical polar coordinates. And I'm not going to derive it mathematically, which you can try out. So the del square, the Laplacian operator, del square, which is the second derivative, partial derivative with respect to position vector, is given by this expression for spherical polar coordinates, r, theta, and phi. So in r, theta, phi, we are doing it in terms of r, theta, phi because you have a nucleus, electron is moving around, and you can assume that it's spherically symmetric. And the potential is spherically symmetric, which means it depends upon 1 by r. Okay. And what I'm going to do is I'm going to simplify this. This doesn't seem to work. So yeah, so you can simplify it using this particular expression. So what I've done is I'm using L square here. Okay, so this particular quantity, that's the L square term. Okay, so the radial part I've taken together. Okay, of course there is an r square here, so it's not completely r independent, but then you have theta and phi term in the L square. The L square will have only theta and phi because r square I've taken it as common factor, right? So as I said, I can run. So this is our expression for the Schrodinger equation, right? We have del square psi plus 2 mu by cross square E minus V of r psi. And psi we are writing in terms of r and theta and phi, as I said, spherical polar coordinates. And I can also separate them radial and angular y. And if you use your previous expression, which is, this expression here, we can substitute it and then get in terms of L square by h cross square and r square. Okay. And of course, now what you do is instead of y, psi, I write r and y and then multiply with r square by ry. Okay. So this is a simple substitution. And if you do that, what you get is a simplified expression where on the left hand side you will see it contains only r. So this is the method of variable separable. So the idea is to separate the r onto the left hand side and the y, which contains theta and phi, onto the right hand side. So now if you look at it, the LHS, that is the left-hand side, is having only R, and the right-hand side is having theta and phi. And R, theta, and phi are linearly independent vectors. They don't depend to each other. And if you have one side only of R and the other side of theta and phi, and since R and theta are not dependent on each other, it follows that this should be equal to a constant. Okay? There is no other way they can be equal because they are linearly independent. So that constant, I'm giving L into L plus 1. Now, why L into L plus 1? Because we already know that it will come out as L into L plus 1. You can give, say, Q. It doesn't matter. But we know that finally, it will have the form L into L plus 1. That is why we are giving it to simplify much easier L into L plus 1 at this moment itself. Okay? Now, so this is the expression we have now. So left-hand side equal to L into L plus 1, right-hand side equal to L into L plus 1, or you can write the radial part as this and angular part as this particular form. So here, now it looks very simplified, and then you can solve it much easier than the expression which we had in the beginning. Okay? If you have any doubt, I can go a little bit slower, but I think you might have already done these exercise, so I'm just quickly going through. Okay? Now let's take the angular part first, which is equal to 1 by h cross square, 1 by y, L square y. And this L square is given by this particular expression, which you already know. Okay? So now, if you write the whole thing instead of L square, you can write in terms of the theta and phi here. And of course, there is a minus sign which goes to the minus L into L plus 1. And we have y here, which is having theta and phi. Okay? And this is, I'm writing it. I hope you know spherical harmonics. Have you studied spherical harmonics? No. Okay. So there are some special functions in mathematical physics, usually applied to physics or physical problems. Now, these are in terms of Bessel functions, Legendre functions, Legendre functions, Newman, Hengel, and so on. Now, the idea about using this special function is you can have a differential equation based on these special functions, and when you see a particular differential equation like this one here, so this is a differential equation, right? This one is a differential equation. So when you have a differential equation of a form which is similar to some kind of a special function, you say that the solution is equal to this. Okay, so it's like you define a Bessel function, right? And you generate a differential equation corresponding to that Bessel function. Okay, second order differential equation. Then you are solving some physics, and you will reach a differential equation, and then you compare with these two, and say that okay, these two are similar differential equations. Which means, since the solution of this is Bessel function, the solution of this will be Bessel function. Is that clear? So that is the idea of using a special function. So there are different special functions, and when you combine, this is associate Legendre function, and with the phi part, when you combine together, you call it spherical harmonics. Okay? And when you have a differential equation like that, you need to know how to normalize this as well. So there is something called a normalization. Why? Because you are dealing with quantum mechanics. Now, when you say this function, you are talking about the y, which is nothing but a wave function, right? And the wave function has to be normalized. Okay? So when you say E psi is equal to H psi, you assume that psi is normalized. Okay? Now, in mathematically, you don't call it normalization, you call it orthogonality. So it's the orthogonality of a Bessel function or orthogonality for an associate Legendre and so on. So this term here, what you see here is the normalization, or how do you find it? How do you find the normalization factor? that you've done in simple quantum mechanics. How do you do it? Integral minus infinity to plus infinity, psi star, psi, d tau. And it should be equal to 1. And that's the normalization condition. And when you integrate it, and when you equate to 1, you'll find some constant which you need to multiply with the psi to get the normalized wave function. And that part is this. Clear? And it comes out when you do that. And that part I'm not mentioning here because it's a bit lengthy, which is beyond the class which we are doing right now. So what you need to assume is using special functions, associate legendary polynomial, PLM. Okay. Sometimes the M is written as a superscript. L is subscript, M is superscript. If there is a superscript, it is called legendary polynomial. If there is a superscript, it's called the associate legendary polynomial. Okay. And the solution of this will be of this form, which will have the theta part and the phi part. And what are theta and phi? What are theta and phi? Theta is the polar angle. What do you mean by polar angle? So suppose you have, so if you look at, suppose this is the, you have the, I should draw it, right? Yeah. Okay. So this angle is theta. It goes from 0 to 180. This is called the polar angle. So it's the 0, it goes up to 180. And this is your R. The length element is the R. This is your theta. And what is phi? It's called the azimuthal angle. Azimuthal angle is the rotation of this. It goes from 0 to 360. This is the phi, the rotation. Okay. So one is this polar angle, and then the rotation in the, suppose this is the axis, this rotation. That is 0 to 360. The radial length, right? 0 to 180. And then if you take a projection, this rotation is 360. That is the azimuthal angle. Okay. So we have these three angles, right? And your solution depends upon the theta and phi. And these are quantities L, which you already have, and you have a new term, which is M, which also comes out by default from the associated legendary polynomial, which is the magnetic quantum number. Okay. So now what you can see here is L is coming out by itself. So in case of Bose atom model, there was no L, right? It was only dependent on N, the principal quantum number. But here you can see that the L comes out by default. M comes out by default. Comes out from the solution itself. So quantum mechanically, you can get these quantum numbers from it without assuming something. Okay. Okay. Now look at the radial part. So the solution we got so this is the solution for the theta and phi, which is called the spherical harmonics. And then you have the radial part with this particular equation, which was the left hand side, right? Again, equating to L into L plus 1. Take L into L plus 1 inside, okay, because it goes for E minus V minus L into L plus 1 and multiply with R. R goes to the other side, and then 2 mu by h cross square, okay, which you have taken it outside. And this is something which you already seen. So now what we have is, you have this part is the derivative part, and this is 2 mu E minus V by h cross square. So this is like energy minus potential. So you have two potential terms instead of one. Okay. One is the electrostatic, which is this one, and this is the part because of the orbital motion. Okay. Okay. So now what you do, so this is some simple substitutions. Instead of R, you write R of R, which is equal to U of R. And when you substitute, it changes to something like this. And then, of course, in atomic unit, you don't use the 4 pi epsilon naught. But one thing you should remember is, whenever you do a calculation, either you use everything in atomic units or you use in the MKS system. When you use the MKS system, you have to use 1 by 4 pi epsilon. You have to add that to the system. Okay? I mean, if you miss that, then you will have a problem. Okay? So, yeah. So the same equation, I'm rewriting this in this form. And now I'm substituting 2 mu E by h cross square, that is this by epsilon square by 4. Okay? So this is the equation I get. Okay. Now one more substitution. I say x is equal to r epsilon. So I'm writing in terms of x now. So the r is the variable, now it has become x. So I'm writing in terms of y. Okay. And finally, you get something like this. Okay. So you get this expression here. Okay. Now, let this be here. Now, look at this expression. Okay. This is not from here. Okay. This expression we have done. This is the radial part. We stopped at this point. Now look at the new expression. Now this is where I said, when you use a special function and look at the derivative differential equation of that special function and you compare. Now you see that they look similar, right? So this is an equation which is already known. This equation is known to you when you do mathematical physics. You know this equation. But then this is the solution we got by doing all those substitution for the radial part. And then you can see that, okay, there's a second derivative minus 1 by 4, and there is a 1 by x term with some constants, and then x square term with some constant, and y of x. This basically compares. So they are similar equations. So now, this is one exercise you can do. If you substitute y of x into this expression and see what you get. Okay. So if you substitute y of x is equal to e raised to minus x by 2, x raised to k plus 1 by 2, ljkx. Okay. And this L is called associated Legore polynomial. This is a different function. It's another special function. And if you substitute it, you will get something like this. And this is associated Legore differential equation. So this is also an associated Legore differential equation, but which is modified. So this is a modified associated Legore differential equation, which is corresponding to this one. Where now the important factor is this j is the Lj, the order of Legore polynomial. K is the differential power of the L, and yes, that's all. So whatever you have here, j and k are actually defined in the Legore differential equation of the associated Legore polynomial. So you can have correspondence between these two. So the solution of radial equation is this. Now this is what I said. So now we know that the solution of the radial part is equal to this equation, because it's nothing but differential equation in associated Legore polynomial with a substitution of this. So that is the solution. And we know that this is the solution of our equation because they are analogous. Now what we can do is we can equate these constant terms. Clear? So that's what we are going to do. So we have this equation. This is the solution of the radial part, not solution. This is the differential equation of the radial part. And this is the modified differential equation in associated Legore polynomial. Okay. So what we have is, we know that L into L plus 1 is equal to k square minus 1 by 4. And 2 mu e square by h cross square epsilon is 2j plus 1k plus 1 by 2. Okay. So this is how you find the solution, because we need to know what are these k's and all in terms of some number. Okay. So now first let's take this part here. So the 4 into L plus 1 is k minus plus 1 is equal to k square. And if you write in terms of k square, this is nothing but 2L plus 1 the whole square. So k is 2L plus 1 because we don't have a k here. So we need to write this in terms of some value which you already know, that is L. So k is nothing but 2L plus 1. Okay. On the other hand, 2j plus k plus 1 by 2 is, instead of k, I can eliminate k by using this value, 2L plus 1. So I can do that, and then what you get is 2j plus 2L plus 2 by 2, which is nothing but j plus L plus 1, and which is equal to the n principal quantum number. Here, I'm not proving how that comes into, but we can, it's basically comes out. Okay, it's a number. Okay, so it's a number which you already have, which is n. Now, if you go back and we have all the substitutions, the epsilon is this particular thing, epsilon square is this, and this is another substitution we did, 2 mu e by h cross square is minus epsilon square by 4, right? And so epsilon square is 2 mu e by h cross square, which is equal to 4 mu square e raised to 4 by h raised to 4 n square. Okay, and if you just rewrite for En, now I'm putting n as a subscript because n can change. So n changes, energy will change for each energy level. So that's why we have E with a subscript n, and then you get this term, which is something which you already know. Okay, because it's hydrogen atom, so we have Z equal to 1. Z square is not. But everything else is known to you. This is called the Bohr radius, which we have already seen from our classical picture, semi-classical picture, and En is minus h cross square by 2 mu a naught square n square. Okay, so this basically comes out from the hydrogen atom problem by solving using Schrodinger equation. Okay. Now again, so we need to look at the equation once again. Here, so the solution is this, right? We said that the solution should be of this form. Now, since k is 2L plus 1, we can write k plus 1, because we have a k plus 1 by 2, right? So k plus 1 by 2 is L plus 1. Okay, and j plus L plus 1 is n, so j is n minus L minus 1. I'm trying to remove all the terms which we don't know. Okay, so I'm removing k and j from the solution, and if you substitute that, you get this expression, which is y n L x is equal to e raised to x by 2 x raised to L plus 1 ln minus L minus 1 to L plus 1x. Okay, and these are Legore polynomials, associated Legore polynomial, which is also known to you. It's kind of a table, you can write it. L01, L02, L11, and so on. You can write. Okay. Now we need to reverse substitute everything back. Okay, because we know everything in terms of y of x, but our solution is r of r. We need to go back to r of r. So you need to do all the reverse substitution, where the last substitution we did was x equal to epsilon r. So if you do that, you get this term. Okay, so epsilon square by 4 is 1 by a naught square by n square, and epsilon square is 2 by a naught n. Okay, so x is 2r na 0, and this you get of this form. So now instead of epsilon, you need to put in terms of r. Okay, sorry, instead of x, you need to put in terms of r. So I'm removing x and epsilon, and I'm putting in terms of r, which is a non-quantity. That is the variable we have used it to start with. So you get u and r is this. But then this is not the end of it, because this is in terms of u. But we know that u is r of r. Now again, reverse substitute. So r of r is this term. So you need to write this expression for R of R. So R of R NLR is A into, because you need to again normalize it, okay, with e raised to minus R by Na0 to R by Na0 raised to L, L 2L plus 1, N minus L minus 1, 2R by Na0. Okay, so if you normalize this, this is the normalization, as I said. Okay, so I'm taking 2 outside, so it is 0 to infinity. Otherwise, it's minus infinity to plus infinity. It's an even function. So you can, instead of minus infinity to plus infinity, you can write 2 into 0 to infinity. And then you can equate all the terms with a constant coming outside. And then you can find that using the gamma function, okay, which is this integral minus Ez z raised to a L a b a z L b a z dz is this particular gamma function, okay, which is gamma a plus b plus 1 by cube by gamma b plus 1. Okay, and if you substitute that, we get this particular, instead of a, what is a? A is your is r raised to, yeah, so you get the terms here from 2l plus 1. So 2l plus 1, then n minus l minus 1 plus 1. Okay, b is n minus l minus 1. And if you substitute that, your a is square root of this term. Okay. All right. So yeah, of course, we know that how to find the gamma function, right? In terms of factorial. So that's how you have this factorial here. And then you normalize the radial function and you get this complete wave function. So this is the radial part of wave function for the hydrogen atom. Okay. So exercise. I mean, most of you might have laptops with you. So you can plot this. Okay. You can find out R10. So how do you do that? So you have N and L. So R10 is the first orbital, N equal to 1, L equal to 0. That is S. L equal to 0 is S orbital. So 10. So R10, substitute that, and then Legora polynomial. If you just search in the Google Legora polynomial, it will give you all the Legora polynomials. So N equal to 1, L equal to 0 means it is 1 minus 1, 0. So this is L0. And L0 means 1. So L01. So that is available in the literature, which you can use, and you can plot this and see how it look like. Okay. So this is only the radial part. Okay. Now we have the angular part, which is the spherical harmonics. So the complete wave function is the radial with the angular part, and it will look something like this. Okay. So if you want to solve hydrogen atom, this is what you get. Okay. And just simple exercise to do. Find out psi 3 minus 1. Okay. Now, I mean, to solve the simple hydrogen atom problem using quantum mechanics, you can see how lengthy it can be, how complicated it can be. But you can exactly solve and get it. But the question is, have you actually solved it completely? The answer is no. Okay. This is only only the beginning of hydrogen atom. Hydrogen atom is much more complex than this. And what is that? Why is that? What is missing in this equation? What is missing in this equation? Spin. Where is the spin of the electron? Spin is not included here. So this is not complete picture. And also, and what is spin actually? What is spin? Yeah. Well, if somebody said that it's the electron rotating or spinning, it's wrong. Okay. Spin, maybe the word spin itself is wrong. I mean, maybe when Pauli used it, he said spin. But the word spin should be written in quotation because it's not the spin of an electron. Because since the electron doesn't have any shape or size, we don't know anything about the spin. So it's not the spin of the electron. It is something called intrinsic angular momentum. Okay. So instead of saying spin, always say spin angular momentum. That gives a better way of, the correct way of saying, because the electron doesn't spin. It doesn't have any spin. It is something called the intrinsic angular momentum. And if you ask me it's like if you ask me what is spin, then I don't have any answer. Because you can't. It's like if I ask you what is charge, can you give me an answer? What is charge? What is charge of an electron? What is charge of an electron? That is the value. But what is charge? I'm not asking what is the value of the charge of an electron. I'm asking what is charge of an electron or any particle. What do you mean by charge? That's easy to define, right? It's an intrinsic property. You can't define these things. You can't define what is the charge of an electron. Similarly, you can't define what is the spin of an electron. It is not spin, it's an angular momentum. So how do you come to that value? The half. Say, you say the spin angular momentum is half. When you do an experiment, to find out the angular momentum of an electron, say electron in the ground state of hydrogen atom, you get the orbital quantum number or orbital quantum angular momentum, which you already know, plus an additional. And that additional, how do you represent? By some intrinsic property, some property of the electron, which you call it by the name spin, because that historically it was called spin. Okay. So, but you have to understand that is not the spin of the electron. That is called the intrinsic angular momentum of the electron. You have an orbital angular momentum because of the electron moving around the nucleus, and there is some motion within the electron itself. We don't know how it is. There is another angular momentum which is added to the total. Okay. And that is important to the spectroscopy as well. That is why I want to mention that spin angular momentum is very important, because maybe in the next class, we will discuss a little bit about the spin part, which will have an effect on the total angular momentum, and that is going to be used in the spectroscopy. Okay, and how it is used, we will discuss that. Okay, I think I'll stop the lecture at this picture. This is the first photograph of hydrogen. This is, well, it's not a photograph, it's a spectrum again, but then this is a photograph, and it's in a paper which is in a PRL. Okay, probably in the 2000 something, I don't know exact year, I forgot, but then yeah. So this is a picture. So it looks something like. Any questions? So what we discussed is two things. One, for spectroscopy, the semi-classical approximation is valid. Okay, to an extent it is valid, but you will see that you need to add spin-orbit coupling, relativistic correction, and so on to get an accurate representation of the spectroscopy lines, if you need to get that. But in principle, the gross structure of a spectroscopy of a hydrogen atom is you can reproduce using the simple Bose atom model without any addition. Okay, and in Bose atom model, the principal quantum number is something which is assumed depending upon the energy levels, but that number is basically is one of the quantum numbers which you see from solving the hydrogen atom problem using Schrodinger equation, where you also get the orbital quantum number, which is L, and the magnetic quantum number, which is M. Now, the next lecture, what we are going to see is, well, we have N, we have L, we have ML. We call it ML. The reason is there is something called MS also, which will come later on. ML. How does a transition occurs, or are all transitions allowed? It is not. So there are something called selection rules to have a allowed transition depending upon. So what we are going to see is only dipole allowed, which basically means dipole means you have the idea of transition from one energy to the other energy level in terms of the N. So the electronic transition. So a dipole allowed transition we are going to look at in the next class. And then we will do, and after that we will continue with the tutorial where we'll do some of the problems which you already seen here, and then some of the transitions, transition lines, and looking at how do you differentiate between one spectrum to the other, and theoretically what is the aspect which make them different, and so on. Okay, that we'll see in the next class and then in the tutorial as well. Okay, so I think we'll stop here. Little early, but yeah. Okay. If you have any questions regarding this, yes.
Comes. Sir, when we previous class, we seen that the energy of the hydrogen atom is minus 13.6 spectrum. But when we start the hydrogen atom by splitting the equation is very bigger form. Why this come?
No, it's not. I mean, if you, I think it's, is separated out of.
It's me.
You're saying this one?
I don't know, this question.
No, I mean, if you separate out the NR, it will become orange. I mean, it looks different, but they are same. You have the Bohr radius, right? So instead of this, you can put the Bohr radius. So it will be like h cross by 2 mu n square a naught square. Maybe there it was a naught.
What keeps in hands?
Yeah, you get the same message.
Which has?
Maybe you can check. We should get the same. Yeah, it's always this. We have then we have put this one. But if you substitute this here, it'll be 1 by a naught square. And so they be similar expressions. I think we have the same expression for the Bohr. We need sure to the parties. Otherwise, you can't use Bohr energy density. It should be the same. It basically they produce the same.
The second, we also covered the solutions of hydrogen atom to dark capers and lighting.
Yes. Yes. This one you can use for. Here we have not included Z. And right. In the mu, so it depends on the mu produced parts. What is different between both? The difference is one is the mu and the E square. E square is the charge. And for everything we say it's E itself, right? But suppose if it's helium, then you have 2Z. It's 2, and so on. So we have not used Z here because I'm specifically solving for hydrogen atom. But in the beginning I said you can solve the same thing for hydrogen light. That is, any one electron system you can solve. The only difference is instead of E squared, you need to write Z E the whole square. What things? Because it's like Q1, Q2, right? Q1, Q2. So Q1 is ZE and Q2 is E. It is. Okay. Anything else? There's not stop here. Yes.
So starting things.
Yeah, please ask that. Go ahead.
I know since bring out if we had an isotope, so can terms of my steady proximity to that like
Yes, see, the spherical symmetry is what you are doing is you are not including, oh, that is one point. We have not included nucleus into the nuclear size doesn't matter. If you look at the picture in the beginning, the nucleus is the point. So here we have not assumed the size of the nucleus. It's not included at all. So even if it's a heavy element, we are saying that nucleus is a point because the electron is much far. So in terms of the distance, you take it as the origin itself, and then you do that. The nuclear size is not coming into picture. The only number of protons will come into picture. So the size of the nucleus is not considered. That is why we can use the same method to solve any hydrogen-like one. The only thing is you have one electron and the nucleus and the interaction between nothing. And the mass will be reduced mass. So that is what the one which is going to affect the final solution. Right? Otherwise it will remain the same. Yes. Okay. All right. So we have that. And then we'll be back at 2:30. Okay. Thank you.
So